Hi, everyone. So this is the ninth class on knowledge graphs, and next week is the last one. I hope you've enjoyed this great set of speakers. We have so far heard about the basics of knowledge graphs, creating, maintaining, implementing. And in last week, we learned about machine learning with knowledge graphs. Today, we'll hear about some very high value use cases. We picked financial services as the vertical because they're relatively new and because probably money is one of the most important creations of humans. We'll now start with JU, Distinguished Engineer and Architect at Intuit. Each speaker will have 30 minutes, and I'm happy to remind each speaker 5 minutes before their time ends. And for the audience, please post your questions in the Q&A tab below and prefix your question with the speaker's name. Thank you. Jay, please take it away.
Thank you, Naren, for the introduction. It's a great pleasure. It's a great privilege. It's a great honor for me to represent Intuit to share our knowledge graph journey. I have been following this class very closely, even though I cannot attend all the classes. I watched all the video. For me, it's a great learning. I learned a lot, and I hope that what I can share can help the class understanding how in our financial industry, we adopt the knowledge graph to help our customer and then also provide business value. So I have quickly, I want to introduce myself. I'm a full stack developer. I've worked on many parts of the end-to-end system stack. I started as a database engine guy, focused on parallel shared nothing database from University of Wisconsin-Madison. And then I started moving up towards more real-world application, including a B2B e-commerce trading platform. And then finally, I landed at Intuit. At Intuit, I worked on many parts of the system, starting from tax engine and platform, all the way moving up to UI framework product. In the last few years, I've been focused on end-to-end data architecture and strategy. And guess what? I started actually taking notice of the advancement in the semantic technology, especially in the knowledge graph world. So now my focus starts switching towards how do we leverage knowledge graph? How do we elevate data to knowledge? So for this particular talk, only 30 minutes, I'll focus really high level about what we are doing at Intuit with knowledge graph. But before we go there, I want to actually introduce a little bit about Intuit. I've been working with Intuit for 17 years. It's probably one of the best kept secret in Silicon Valley. We're not Google, we're not Facebook, we're not Amazon, but we're in a unique position to help millions of customers. Our mission is to powering the prosperity of the world. That means no matter where you are, whether you're financially strong or when you need help, we can always help you to improve your finances. Today, we're actually doing that via our flagship products. We have TurboTax with more than 50 million users. We have Mint and Turbo, and give you a holistic view of your finances by aggregating data from all our partners. We are helping our small business customers, both self-employed or small business, ranging from mom and pop shop all the way to 100-person companies. We're helping them not only with their accounting, but also help them with their payroll and payment and running their business day to day. We also actually supply software and services to more than 600,000 tax professionals, CPAs, and to empower them to help their customers. We also package their expertise in our product offerings so that when people are stuck using our software, need some additional help, need human expertise help, we package that service within. Also, we partner with many financial institutions. Two of the guest speakers later is also our partners. Because we not only integrate data from their financial institutions, but also we repackage and resell their services, because at Intuit, we don't offer everything people need in order to advance their finances. Ultimately, our goal is to make sure everybody we serve can get more money with minimum work and with complete confidence. That's really a tall order for the world. And then we're trying to do that in the new age of AI and machine learning. We want to do it in an AI-driven way. We want to transform ourselves from a product company, that's what we know today, into an AI-driven expert platform. So let me give you an example of what does that mean, and that's actually has a close tying into knowledge graph. What I'm going to share here is really a pre-recorded video demo showing one of the latest innovation features we have in TurboTax, which is in the form of TurboTax Assistant, a really intelligent chatbot bot can help you understand how we actually calculate your return. So here's the recording.
So here we have TurboTax Online, and you can see the user owes $12,743. So let's see what Annie's experience might look like today with the new Explain Why answers integrated in the TurboTax Assistant over here. So let's ask the same question that Annie asked. Why do I owe so much? And see what the Explain Why answer is. Well, here you can see the assistant didn't quite know whether she was asking whether she owes the IRS or whether she owes to pay for TurboTax to file the software. So in this case, we are presented with two answers so that we can choose which one we mean. In this case, let's choose what Annie meant, which is why does she owe the IRS, and see what Explain Why tells us. So here you can see Explain Why gives her very personalized data with her exact amounts that she owes and why she owes. And it comes from the $24,000 she's supposed to pay for the year and minus the $9,000 of tax she's already paid and the $2,000 in credits she qualifies for. Now what's interesting here is Explain Why also has drill downs into how it came up with both of those calculations. So we can actually drill down on how they computed the $24,000 she's supposed to pay. So let's do that. And here you can see that Explain Why answer for why she owes the $24,000. Now let's go back up and see how the credits were calculated. And here you can see the 2,000 credits she qualifies for comes from her child and other dependent tax credits. So here you can see it's very engaging for the user. They can continue to drill down further and further with Explain Why answers, and they're getting personalized data that applies directly to them. So this is more engaging with TurboTax and gives us personalized data.
Awesome. Hopefully you get a glimpse of what we are doing. Provide a really intelligent TurboTax Assistant experience to our customer. This whole experience is a great example of what we mean by AI-driven platform. The TurboTax Assistant is really intelligent, it's personalized, it's really tied to your specific tax situation, and explaining in detail how we come up with your return. And it is powered by our tax knowledge engine platform and the conversational UI. Underneath it, there's actually a tax knowledge graph I'm going to share a little bit later as one of the first use case. So our goal is to provide personalized experience to help people with their taxes or finances, make sure it's done right, accurately, but also with minimum effort and as well as complete confidence. Before we go into the use case, I actually want to take a detour a little bit here because this question about what is knowledge graph, we have many definitions. Earlier speakers, from the previous class all have their own definition, which is all good. All the definitions are correct. The question is, there's so many definitions, very hard for people new to the domain try to get a simple answer. What is knowledge graph? So I took an approach. We just take a look at the dictionary items for knowledge. What's the graph? And then we come up with our hopefully common sense or inclusive definition that we can easily rally our engineers, our business folks at Intuit and beyond. So this is how we explain what is knowledge graph. A knowledge graph is nothing but a graph representing data or knowledge in terms of data. Data could include facts as well as information. But also it's beyond just data. We believe logic is equally important. Logic includes conditions, calculations, rules, especially in our compliance domain space. And we organize those into concepts as vertices and relationship as edges. And this knowledge graph needs to be continuously, not only created, but also needs to be continuously maintained, enriched, and curated from experience and learning. And that of course, it's used for understanding and reasoning. That's a big part of the knowledge. How do you use knowledge to solve real problem? But also it's important to realize this knowledge graph is used for both human and machine. We also believe knowledge graph is a connective tissue to connect the different aspects of AIs together. No longer we need to pitch symbolic AI versus machine learning. They all have their own role and they need to be actually connected together. And we believe connecting together will actually provide a lot more benefit to a real world adoption of these technologies. Ultimately, we believe knowledge graph is a combination of both data knowledge graph and logic. So this is where I'm going to share the two use cases in those two areas. I'm going to start with the text logic graph, which is what we call text knowledge graph. And then I'm also going to quickly touch upon a classic textbook example of entity resolution, how we do it, why we do it, and what's the different approaches. We have many use cases like a customer 360 fraud detection and so on and so forth. I don't have time to go through them, but those are very typical use case of knowledge graph in practice in various industries. So let's go to the use case number one. How do we use knowledge graph to help with text programming? Let's first talk about what's the big challenge. There's a famous quote from one of our founding fathers, Thomas Jefferson, talk about in this world, nothing is certain except death and taxes. But little does he know the US tax code could be this complicated this many years later. This graph was produced back in about 6 years ago. Back then, in order to explain the federal tax code, we need more than 64,000 pages. The latest is already well exceeding 18,000 pages. And that covers thousands of tax forms and worksheet. And underneath it has to be translated into more than 100,000 of calculations with more than 500,000 fields. That's extremely complicated. The logic changes yearly, but also can changes anywhere in the middle of the tax season because of late tax legislation. So that means we need to be able to respond to those changes very quickly. And also in order to break down the complexity for our users, because our goal to make a tax so easy, you don't need to understand anything about tax laws or anything about tax jargons. In order to do that, we have to translate that into more than 50,000 screens. So the biggest challenge is how do you scale the development of such logic, to develop, to test, to deploy, and to maintain at that scale, but also try to meet our new target to create a highly personalized experience to get taxes done with high accuracy, with minimum effort and high confidence. So that's really the challenge. Now, if you look at this, is actually, I'm going to provide some very simple examples to illustrate the concept patterns. I don't have time to go through a lot of details. This is actually 3 instructions from federal 1040 tax forms. If you look at it, you may say that's not too bad, right? If you can hire a bunch of programmers, look at the instruction, you can talk to the tax domain experts, say, hey, I need to codify this logic. I can use a procedural programming language to codify line by line what's underneath those instructions. But imagine you have to do that with that scale of amount of, the total amount of the text logic, the instructions, the rules itself becomes gnarly. And also because a lot of tax domain expertise, they are not experts, they're not trained as programmers. So using a procedural programming language, you can easily lead to basically spaghetti code. A code is very hard to test, very hard to maintain. And then also because it's in the procedural programming language, you require the entire application needs to be executed from top down, following exactly all of the instruction or those programming statements. So even if you change a little bit one variable, you have to rerun the entire application in order to calculate the result. In order to make sure the tax return result is accurate, you have to making sure you actually have all the inputs collected. Imagine you have that many of the inputs. How do you know which one is relevant or not? That becomes a very challenging thing. And finally, remember the demo I just showed, we can actually explain to you how we calculate result. Think about if you're using this approach, how can you do that? Because all the logic is all implicit, is all hard-coded inside, locked inside the procedural programming language, at the mercy of whoever did that, whatever the particular sequence for loop they use. How do you explain in a human understandable way? And that becomes a huge challenge. So these are the limitations of the procedural programming approach to solve this problem. So let's take a look at it. What if we actually take a different approach? That's why the team has been working on that in the last more than 5 years. And then we took a slightly different approach, which is really knowledge driven. The idea is we can analyze all the text domain instructions, extract essence or patterns of those calculations. And we use this term called generic calc pattern. It's called GIST. GIST is some generic thing to describe the commonly used patterns in the calculation. In this case, I use the example of add. You know, if you look at line 19, the instruction says add line 17 and 18E. So in that sense, there's a concept called add. It can add multiple lines, it can have multiple inputs and produce one output. And why don't we actually make that as a meta level schema, or maybe you can call it ontology. We try to avoid the use of the word of ontology, but that's the essence. What's the generic pattern in the whole entire tax return? The team came up with probably only between a couple of hundreds of them. It's now, you know, 100,000, thousands of 100,000. And then the job for tax domain expert is how do you describe those instructions using those patterns in a declarative way? So in this case, for line 19, you just say, oh, I'm actually recognizing line 19 is using this generic concept called add. I'm gonna bound the input to line 17 and bound, and also line 18E. I'm gonna bound the output to line 19, and that becomes our, the actual description of the calculation. And we can do that for the other statement. Now, if you do that, then the whole calculation is nothing but a graph. You can stitch them together. And so what's the benefit of this approach? As I just described, it's very declarative. You don't have to understand a procedural programming language, the statement, the if statement, the for statement, for loop, and so on and so forth. You focus on what patterns I can match to, right? And also it's by design, it's very granular. You only focus on one statement at a time. You don't even worry about their sequence, because when you stitch them together, the sequence is already built in as a dependency graph. You can incrementally compose those individual statement, individual modules together to form a bigger graph. And finally, the explanation is built in. Let me explain a little bit, what does that mean? So for example, if the same calc graph tree for the simple example we have, if you want to explain how you come up with line 20, then all you need to do is analyze your knowledge graph saying, hey, which calc node actually produce line 20? In this case, there's a calc node, a GIST called subtract. Okay, I'm going to just actually explain what that calc node is really about, right? It's a result of subtracting, you know, line 16 from line 19. Okay, if I want to actually know a little bit further, I can drill down further. I'm just, you know, traverse the graph backwards, starting from the specific place you want to explain, and going back, chaining those calculations to explain what happened to your tax return. Of course, right now, as I just showed here, even though this is understandable, it's still far away from what our end user really wants to see. Remember from the demo, it's a lot more natural. There's a lot of innovation we did underneath it to make sure the explanation is very natural to a person. So now we covered the calculation, which is a big part of it. The other generic pattern we discovered in the tax domain are those rules, those interesting rules called eligibility rules. And this is a simple example. This particular rule have two parts, right? Literally saying if you are you need to be a resident of California and you need to be older than 18 in order to be qualified for this tax benefit. So with that kind of a, you know, rules or decision tree, we can use the same approach. We can construct a knowledge graph about this decision tree. Has a start point, and also had endpoint. Endpoint in this case is only two possible end result, right? Whether it's qualified or not. Anything in the middle is really all the variables, all the data nodes involved, all the condition needs to be computed. And what is the flow needed in order to reach to one of this, the end state, whether it's complete, whether it's qualified or not qualified. Now, what's the benefit of taking this approach? Now you can start reasoning about the graph backwards as well. You know, given you know already something about this person, do you know what information is missing before you can conclude and reach to one of the end state? Or you have enough information to make the determination? So this, in this example, what if we know this person already is 17 years old? Do we still need to know where they live? In this case, no. By analyzing the graph, you already conclude there's no need to collect any more information because you already know the answer. So this is actually one of the key things behind how we can make our experience really personalized and relevant. We only ask minimum information needed in order to reach to a particular outcome. We're not going to collect all the information up front because a lot of those may not need it based on your situation. So putting things together, so far I talk about calculation graph, I talk about completeness graph. So we need a text engine, knowledge engine to glue things together, to import a text knowledge graph, to bind with the user's tax return data. And then via that, we can find out what information is still missing in order to reach the final outcome, which is in this case, compute your refund. And also via the knowledge graph, we can actually do validation and consistency check to see maybe the information you enter is, it's inconsistent, there's an error. You can go back, fix it. And these got, feedback to the application UI engine, which collect more data. And then basically we'll add more data into the user data repository, then load into the technology engine again. We can repeat until we reach to a state we can actually complete the tax return. When we reach to that state, we know via the technology I just shared, we can actually go back to explain, how we actually come up with the answer. So one of the key things about this approach is how do you build the text knowledge graph? Even with all the declarativeness, all the patterns, there's still a lot of human effort needed to build that. And that could be very tedious and error prone because of the scale of our domain. So this is actually where we actually also be able to automate a lot of those generation, because again, we already have the generic patterns in the calc. So what we could do is using natural language processing to extract key terms from those instructions. And then we actually literally, we can do a semantic pattern matching against all the patterns we know. If there's a match, we can start actually producing a concrete calc. So in summary, we actually took on a different approach, a knowledge graph approach to handle the text programming logic. I already shared a lot of the benefits there, but the other thing I want to actually point it out is besides, being declarative, because being modular, because besides, if there's built-in explainability, it also helps drives dynamic user experience to minimize the questions we need to have answered. But ultimately, it also targets towards the domain experts so that they no longer have to learn about specific programming language to translate from a high level understanding and knowledge into a much lower level, procedural programming. They can actually use on knowledge-based tools to specify all the logic. So this is some early result. Even 5 years ago, after we deployed that, we immediately see 50% reduction in one of the most complicated forms. People have a lot of questions about W2. Also, more than 3/4 of the customer found it's extremely useful for the explain why feature. So I don't have a lot of time. I'm going to quickly go through the entity resolution. This is something already covered in multiple talks. I just want to show what unique approach we took. The big challenge is data always have silos. A silo data means you have different ways to represent the same data, same value. The question is, how do you merge them together? By the way, data silo is not necessarily a bad thing. Usually there's a reason for them to exist. Sometimes it's because of acquisition. Sometimes it's because different teams optimize for their specific use case. The question is, how do we solve that? One of the first steps, no matter what we do, is we need to standardize them. So in this case, I have the 3 different representation. I standardize on names, standardize a value format, so at least I can compare. A traditional approach, again, is I can write a program to do a pairwise comparison and using some algorithm, and then try to compute a similarity score between any of the 2 entities. Then I could use them to start merging. In this case, I'm able to merge 2 entities together. I mean, reduce down from 4 all the way to 3. But after merging, I'm not done because the merged entity has new attributes. I need to recalculate to see if that's get connected with other entities. So net after a couple of iterations, I'll converge into a final solution. In this example, everything got converged into one single customer entity. So there's a bunch of limitations to this approach. It's procedural, it's very purpose fit. It's actually iterative, and also it's black boxing. It's hard to explain, except for the programmer who wrote this code can explain what happened, what technique they use to do the entity resolution. So what about the knowledge graph approach? So this is what we actually just implement that recently. So the idea is, why don't we define an ontology about this attribute? This is actually a simple representation of what that looked like. A customer have name, email, phone. And each of those, there's actually entity nodes, there's actually attribute nodes. And then we started loading, converting our data, load data into a graph database systems. And it literally is the instantiation of the ontology. After you loading all—
Jay, you have 5 more minutes.
Thank you.
Thank you.
After you loading all this, you have a complete graph, and a lot of those connections are already made for you, right? If 2 entities share the same attributes, somehow they're already connected. Then you can actually use graph analytics and inference. You can start detecting whether any 2 entities may be similar to each other. If that's the case, you enrich the graph with same as relationship. And by having that, then can you start merging? And the way we choose to merge is not physically merge those entities, but create a logical node on top to cluster those together. And you can see there's a lot of advantage of semantics being preserved. It's declarative, and also there's actually visual explanation. If you use graph visualization, you kind of understand, yeah, I can see how these things are connected to each other. One last thing is equally important. No entity resolution is 100% correct. That means you have to take feedbacks. Feedbacks could from customer support engines. They detect, they notice these 2 should not be the same, or a data quality analyst, right? So the minute they detect that, they can actually enrich the graph as well. Say, hey, these 2 nodes, I'll add a relationship. I call them, they're not the same, right? They should not be merged. With that new input, when you rerun the algorithm, it will break the cluster into 2 different clusters. So again, if you look, compared to the 2 approaches, there's pros and cons. But in this case, we actually decided to take a hybrid approach, because the procedural approach, the batch-based approach, worked really well when you first to solve the bootstrapping problem. You have terabytes, petabytes of data in the lake. You need a starting point. So the batch-based processing will help you to build the initial graph, while you use, then you load into a graph database system to do incremental updates to resolve entity in real time. So we actually able to accomplish, even with much simpler algorithm, not as sophisticated as some of the things shared early on in this class, we're able to already accomplish this result. In summary, what are the key takeaways? Knowledge graph is a very natural fit for many use cases. Making sure you don't only just model the data, but also model the logic. We actually accomplished great success by doing that against text programming logic. Knowledge graph can be constructed automatically via human involvement as well, can be enriched. And also the reason we are able to deliver personalized experience is because there's actually text knowledge graph and text knowledge engine underneath it to drive the experience. Before I actually finish, I do want to actually have a provocation here. This is not my work. This is from Dan McCrary, who is a distinguished engineer at Optimum, the advanced R&D lab behind United Health. And he basically is saying, I think this has a lot of, basically I see a lot of similar posts out there, is we believe knowledge graph at the core of the 3rd era of computing. Think about knowledge graph is one place you can actually bundle both human expertise, machine expertise, or machine learning. You can keep enrich it. You can provide not only answers with explanation, but also you can have a lot more knowledge. With that, I think I'm done. Thank you so much for listening to my use case talk. If you're interested applying knowledge graph technology to help us solve even more challenging problems, please let me know. Thank you. That's the end of my talk.
Thanks, Jay. Very, very nice talk and very timely, very relevant because we're all filing taxes. And while you file taxes, we'll think about these things. Next, we have Apur Saxena, who heads JPMorgan's newly created Silicon Valley AI team.
Hello. Thank you, Naren. That was pretty impressive. I'm looking forward to using some of the AI that you show, Jay, on my next tax filing with Intuit. So, can you guys hear me well?
Yes, we can hear you well.
So let me share my screen quickly. We can go. I'm assuming you guys are able to see my screen.
Yes, we can see it well.
So again, as I will double down on what Jay said. As I was preparing for this conversation, I was thinking about, I went to some of the earlier videos and I could not agree more on a lot of the themes that have been spoken about from previous speakers. And so what I will do in this talk is to walk through and wherever I felt that this resonated with us in terms of our own experience doing something at JPMorgan, I'll highlight those as well. As a form of introduction, I've been with JPMorgan at almost 2 years, 1.5 years, or whatever, 20 months, I should say. Who's counting? But I came in from Google, where I led the cloud AI team, build that team up. We focused on building AI products and AI solutions at Google, and something very similar now. Rather than doing it for generic, I do it for the financial domain. That's my background. So some of the products at Google that have huge knowledge systems creation work was around the contact center AI, applying AI to Google AI to contact centers. Knowledge discovery API, and a lot of NLP products that I launched there. So coming with a bit of a product background, how to build and challenges that we have found customers encountering as they use and build these knowledge systems. And similarly at JPMorgan had similar experience. Quickly, my talk is going to introduce you about JPMorgan, how knowledge graph journey and usage has been at JPMorgan. It's surprisingly not very distinct and different from Google's own experience in knowledge graph. I'll share some light. I will talk about few use cases related to the financial services, but deep dive on one and highlight some of the challenges that we faced and answers that solutions that we built on our own. But something that resonates with a lot of the things that were said before. And then talk about some of the future applications and lessons that I've learned over the years in building these knowledge systems. So JPMorgan Chase, those of you who don't know, is the #1 bank in terms of the size in the US and #5 globally. 50% of all US households have some form of relationship with Chase, mostly through credit card or checking account. It's one of the top 3 biggest asset manager in the firm. It's a full service bank, so you get to get all flavors of a banking financial service. So $2.6 trillion in asset and wealth management. And this is, again, a lot of applications where we are using knowledge graph, and I'll highlight some of those as well. So global firm, in terms of volume of data that we handle, is tremendous, and that gives us an opportunity to gather a lot of data and then use that data to form informed decisions around fraud detection, credit decisioning, and so on and so forth. So that's the size. So how does JPMorgan, as you can imagine, like any other bank, I always used to say this, financial services uniquely positioned as a vertical because at Google I work with different verticals, AI applying in healthcare, AI in finance. And we always found finance to be one area where it was easiest to sort of monetize your AI application. And the reason is the people who own the data in financial services can have huge incentive to monetize it. In other industry like healthcare, the owner of the data typically don't have incentives and you have an agency problem. So as a result, the banks, almost every Wall Street firm has invested tremendous amount of money and resources and investment over the years in building their data systems. But most of this is, as you can imagine, is tabular. Knowledge graph had a huge sort of upswing before deep learning took up when symbolic systems were still in a major force. And then a lot of the banks stopped significant investment in knowledge graph. And as you can imagine, it's coming back in big way. So knowledge graph traditionally have been used in fraud and risk management, the classic use cases that you probably hear in textbook or anywhere in the financial industry. But what has happened in the last 2 or 3 years, investment in AI, whether it's knowledge creation for helping the agent in answering customer call, and the example that Jay just talked about in the previous one, very similar. Using event-driven knowledge graph for using alternate data to create alpha. That's another big area that has tremendously increased. And again, this has increased not only these techniques have improved tremendously, especially in NLP accuracy, and that has started generating new insights and new ways of using knowledge graphs. Expanded use of fraud and risk management, another area. Again, we will touch upon some of those in this. And security also has been traditionally not specific to banking, but in banking, the applications have been mostly around exfiltration of data looking at network traffic. In fact, some of the cool videos that I had for this lecture, I could not share because our security would not allow that video to be shown outside. It detects what traffic is going over the network. But having said that, I'll deep dive into one very important effort that Naren, who is he's also leading at JPMorgan, which is building a knowledge graph. Again, company had a knowledge graph which was built before, but was very used mostly for risk assessment. What does that mean? It's essentially understanding who the connected associated other companies are. So for example, in this case, when you're providing a loan to a company, JPMorgan will typically ask a lot of information about who their suppliers are, who are their customers, and so on and so forth. So a lot of this information was sitting in various form in data siloed across the firm. And the first attempt was just building together a connected graph of companies and their associated supplier. And that was extremely useful in recent COVID-19 situation where we use extensively to leverage this knowledge graph. But as you can imagine, those are very limited use cases. So one of the things that we started off is building and enhancing this knowledge graph for a lot of other purposes. It's like any other knowledge systems, you just first start asking the questions. What are the outputs do I need from this knowledge system? And then we did the same thing, came up with a list of questions that are relevant for our customers. In this case, the customers are underwriters, customers are risk management folks, customers are people on the sales side looking and working with the customers directly. So those are the customers. And what are the questions they typically ask is for example, in Boeing recently went through a pretty bad time. The stock went from $216 to almost $90. It was very close to rumored to almost go bankrupt. And before the Fed came in, a lot of questions that were asked at that time was, who are the vendors and the suppliers? Which of these suppliers are JPMC clients? And and how many of these are applying for loans, especially with the PPA. And so as you can imagine, these are very simple to answer questions if this information is already embedded in a knowledge graph by simple link traversal. Other slightly difficult questions, slightly different questions, I would say, is asking questions on what startups are most, have attracted the most influential investors. And I guess there was a whole conversation about this. How do you define influential investors? And there are multiple signals you can use to define influential investors. It could be number of startups they have invested, the quality of the startups, and so on and so forth. And this is where we are using PageRank to understand and come up with those answers. Other examples that we have started looking at to answer some of these questions are the weak link detection problem. Essentially, this happened a lot, more than you think. Typically, there'll be a supplier, one or two, which is a weak link to which almost every other supplier is connected. And if that supplier goes under or is in financial trouble, then can systematic risk to the overall industry or a sub-segment of the overall risk industry. And that is needed not only for just knowing, but for regulatory purposes, the bank needs to know what are the risks and report that to the regulators. So that is one other example where we use the weak link detection. I think this was talked about in the previous slide, one of the last two lectures on graph embeddings and node similarity. Again, a newer techniques that are coming up where you can figure out what are the companies similar to Okta. So for example, you probably heard recently situation around Zoom and Zoom Technologies, two companies which were similar names, and they were a lot of algo traders started shorting or investing in Zoom technology, even though it's very different from Zoom, the video company which we are right now. So this happens more in much more real situations than most of us think about. Link prediction is another classic example. So if two of the suppliers are our customers who potentially could be our next customer is another one. A classic example of using knowledge graphs, machine learning to predict what additional edges will be coming up. And the last one, in fact, community detection or cluster, understanding who are the investors that co-invest. This is again very useful for us from our investment banking arm. So those are the set of questions, as you can imagine, again, should give you a flavor of how banks are thinking about using knowledge graph to answer these questions. So other challenges, again, a lot of these have been already touched upon. So I would not go in a lot of detail. We'll just highlight similar problem exists and very similar techniques have been used at the bank to address those. So as you can imagine, for the structured data, our typical sources, banking again and financial industry in particular, is very data rich with numerous information providers who provide APIs or data that look at various aspects of a bank. And a big part of building a knowledge graph in a bank is ability to connect with all these myriad sources of data and alternative data. And that's where we spend a lot of time. But when you do that, one of the big challenge is understanding and identifying the company name. And again, very classic problem. And this is uniquely, examples here show PayPal. PayPal is known by so many names. And then PayPal again gets acquired, how it changes its name. And that has, JPMorgan itself, for example, was known as JPMorgan, and now it's known by JPMorgan Chase. So that is a classic problem of resolving entities. The second other problem is on the unstructured data side. This is traditionally has not been used to build knowledge graph systems at the bank, because one of the things you need to realize, and this is when I contrast this with knowledge graph that Google built from web data versus knowledge graph that JPMorgan builds, very, very different use cases. Here, the attributes that we define for a knowledge graph are very well curated, managed, and a significantly smaller number than what you will say in a knowledge graph that Google has created. And the real reason here is the decisions that you're making from this knowledge graph have huge implication, and sometimes often have regulatory implications. So ability to justify why you denied a loan to a company, you have to be able to explain that, and if errors made in that has huge implication on us. So as a result, the way we create knowledge graphs in the bank is significantly different from the way we used at Google. But here in this case, again, the classic problems of name entity recognition, entity linking are the similar. We have multiple data silos in the bank. As you can, hold on. Just give me 1 second. As you can imagine, and the problems are the same: NER, entity linking, and relationship extraction. And this is where I think I will touch upon this a little bit later. How you, as you define new attributes, how do you find the training data to build your models to extract this information is going to be key. And how you invest in your getting the training data, how you make that low cost is going to be is a big differentiator for us, as an important investment for us. Going on, so another example that is unique, again, not unique to this knowledge graph, but this is pretty unique for us in terms of example here. L Brands looks to sell Victoria's Secret to private equity firm Sycamore Partners. So there are multiple challenges here. Like temporal is a big one. A deal that could happen today can fundamentally change the nature of the relationship, and how the team, whether the team got completed or not, has huge implication in terms of the relationship between the entities described here. Other thing is authority of data source. So again, we have curated a set of sources from where we populate our knowledge graph. But you have to be extra careful in terms of fake news and nature of the web, especially any web data is highly adversarial in nature. And how do you curate that? Traditionally, the banks have not used those to populate our knowledge graph. Even if you use the use case that we use, that information is highly limited and restricted. And the last bit, like one of the example I would give of ever-changing nature is in the regulatory environment. If you heard about the London whale incident, after that LIBOR, which was essentially a interest rate that was determined by banks getting together, was discontinued and replaced by SOFR. That has huge implication. And if you imagine, if you build a knowledge graph using LIBOR as one of the attributes, you literally have to rewrite that knowledge graph as that regulation changed. So those are some of the key challenges that we see, and essentially all related to dynamism of the information that we deal with, especially with companies. And that has created unique challenges. And that also requires very sophisticated data quality checks, some manual and a lot more automated to address those challenges. Other area which was, I think I did not appreciate till I actually came into the bank is the access control. And this is, again, related to how the banks are use information and collect information. As you might have heard about the Chinese wall. So information that is gathered on the buy side cannot be shared with the sell side. And so typically the solution the banks have come is they are completely siloed data, but that causes a lot of problem in terms of missed information, incomplete information, and inaccurate information. So we embarked on an effort to sort of join these, but also associated we needed to do was impose rules to enforce the Chinese wall between the buy side and the sell side. Beyond the regulatory, other things to note into account is, for example, our Chase side, which is our retail side, has amazing amount of credit card transaction data, but legally our asset management side is not allowed to use that information to derive insights. And this is mostly in some cases organizational boundaries that we have to adhere to because of implication of adverse effect on customers' trust, in some cases regulatory. So imposing that is and how you, even if though you build the same knowledge graph, how do you impose those based on the rules and the roles is critical. And even if you have access, you don't have access all the time. Classic example is information that the company provides to us before the earnings call cannot be shared till the information is available and till the earning calls is released. So that's another example. And one of the challenges we found that a lot of the commercial knowledge graph providers don't provide a very good node and attribute level access control. And this is where we had to go through a lot of sort of workarounds or build systems outside the knowledge graph to impose these restrictions. So again, if you are a startup looking in this space, this is probably an area that we would love to see more. Other part, I think this was, I wanted to bring this up was who uses your knowledge graph and who is querying your knowledge graph. And I think there was a need. One of the previous speaker highlighted the use of building sophisticated user interfaces for querying the knowledge graph. And in the challenge for us was a lot of the business users who are using this knowledge graph are not very sophisticated. And in this case, our knowledge graph was built on Neo4j. And Cypher, the querying language, is pretty difficult for them to understand, even for data scientists in some cases. So forget about business users. And so this is where one of the things we did was to use natural language query and convert that into Cypher queries. And this was work again done by Naren and his team. And this is where we essentially build a table-aware BERT encoder to convert natural language query into Cypher queries. And other key points here is you will get this wrong often, and interpretability is important in these kind of situations. So the way we design the user interface is, as we convert the natural language query into a Cypher query, we give the user the opportunity to modify the query if some of the entities or some of the names are wrong. And that gives a level of confidence and trust that is needed, and that feedback is used to improve the query over time. So, that is essentially the set of things, deep dive into how a company knowledge graph was built within the firm. And of course, it's a continuation of years of work, and we'll continue working on it. The next set of use cases, I'll quickly go through. I won't deep dive into those. Here, these are classic fraud and risk management use cases. And so one clear example, we built on the fraud side, built a bad actor knowledge graph, essentially looking into account, for example, in this very simple use case, you have two credit cards which have opened with the same email address. And as more accounts, customers get added, and over time, if one of the customer transactions are declared fraudulent, looking at the knowledge graph, you can easily detect where these clusters are coming together, and then and flag the other potential fraud cases in future. That's one very common use case. Other thing that we have used very extensively, saved millions of dollars for the bank, is adding new attributes over time. So for example, in this case, we start very simple 4 attributes: name, SSN number, phone number, and email. But as we add new attributes like home address or device ID, that gives you a unique way to look and identify fraud. A lot of the fraud is associated with the same device ID in this case. So as we understand, as we monitor our fraud activity, and if we realize that there's a common linkage on the device ID, we are able to detect significant fraud and flag those fraud use cases. That's another very real example of how we use device ID to detect fraud. So what are the future applications? Again, as I said, knowledge graphs are being used extensively across all the applications. Question and answering is another good one that we are increasingly investing, especially on the customer call center what we call virtual coach knowledge system development. Another one is increasingly you will see is recommendation system for better marketing. So this is an example coming out from our loan department, where auto loans, people who are connected to each other and make a purchase on a car and similar other products like insurance, can we come up with better way to recommend either a car loan or recommend to affiliate insurance that they can buy. Again, recommendation systems are increasingly using this knowledge graph. There are quite a few successful use cases, and this is something that we plan to do at JPMorgan as well. So I will end with some of the lessons that, again, have been said in some form or the other by previous speakers, but has over the years have taught me a lot, and also the teams that I've worked with. And any knowledge system has to be built by has to capture the knowledge, and in a lot of the use cases, the knowledge is not with the data scientists, the engineer, is with the domain owners or the business owners, and capturing that information consistently, iteratively over time. You have to invest in building the right tools that a non-technical staff can use. So for example, in the case of Google Contact Center AI, we build a whole set of collaborative tools for capturing knowledge from a call center agent and feeding their knowledge system. We are doing something very similar here. Here, the users are also the call center agent in some cases, or portfolio managers, asset managers in the other cases. It's not a one-time process. Again, it's a continuous process. You have to build the tools accordingly. I think another key metric.
Apurv, you have 5 more minutes.
I'm almost there. In terms of optimizing knowledge systems, you have to optimize on identify key metrics that you will optimize on. Otherwise, you can do a lot of experimentation without actually improving the system. So for example, in some cases, did the agent use the suggestion that the knowledge graphs, knowledge system came up with is a metric that we optimize on. Or in the case of quick Q&A systems, that the user used that answer is another one. Interpretability is a huge example. I think we just saw an example from Ray on this. And ability to provide feedback, and that feedback being used is an important part of building trust with the user. This is where a lot of knowledge systems, in my view, fail. And that if the linkage is not there, you will see dramatic reduction in the usage of the knowledge system recommendations. And I think the last one is pretty generic, like any other. Training data beats better models over time any day. But I think one of the speakers talked about using Snorkel active learning, especially to reduce the cost of collecting training data. And that's one of the another case we are using as well here at JPMorgan. So those are some of the big lessons I learned. I'll pause there for question at the end. We are based in the West Coast in California. This team was created almost 18, 19 months back to focus on building AI systems and AI solutions for the bank. We always are hiring, even in this time. So if you are interested in learning more about how we are using AI beyond knowledge graphs, please ping me or Naren on our LinkedIn, and we will be happy to connect with you. I'll pause there and back to you, Naren.
Thanks, Apurv, for a very insightful talk and for exposing the audience to problems in the financial services industry. With that, I will turn it over to David Newman, who leads the Knowledge Graph program at Wells Fargo Bank. David, over to you.
Okay, thank you, Naren. I hope everyone can hear me.
Yes.
I'm going to launch my deck now. Okay, great. Well, Apurv, Jay, you guys are a hard act to follow. Really interesting things that are being done at JP, MC, and Intuit. What I'm going to do is talk more conceptually than operationally in terms of what we're actually building and deploying in Wells Fargo but I hope this will be very interesting because I'm going to cover a lot of information. So yes, as Naren mentioned, I lead the Knowledge Graph program at Wells Fargo Bank. I also chair the 5.0 initiative for the industry, which I'll describe as we get into the presentation. So what we're going to get into a bit first is a description of Knowledge Graph as a paradigm shift for the entire enterprise. It really is a major tectonic change for how we work with data. I'll go into that. I'll talk a little bit about the architecture of what a Knowledge Graph environment should look like. And then I'm going to drill into some more detail about the primary use case around a semantic data catalog. But let's first start off with business users will have some major concerns with data to start off with. How can we significantly improve the accuracy of our metadata, as well as reduce the tremendous overhead and costs when it takes to search for data, particularly data wrangling and data science needs accumulate tremendous amount of time. How can we reduce that? How can we, by gaining a better understanding of the inventory of our data sources and elements, how can we reverse the rising costs of data governance and management? How can we essentially maximize business value and insights from the ever-growing volumes of data that proliferate across the enterprise? And how can we better ultimately link information from diverse sources in order to produce holistic views of customers and other key data areas? So in terms of background, there are many kinds of data management challenges that the enterprise faces by leveraging conventional data technologies. Typically, most organizations are highly siloed that produce data as a result of organizational changes and M&A. Many of the dictionaries and glossaries that are developed by these organizations are highly incongruent. And then lastly, as we all know, there's a massive explosion of data. But we have many challenges with the legacy data management capabilities, the paradigm of relational database management, which is actually now 50 years old and it's somewhat aging. We need something different. This current data legacy world produces many incongruent data models as a result of the high siloed nature of organizations. There's an explosion of labels that reflect columns. We have insufficient metadata. And again, many of our data platforms are highly siloed, as well as many of our vendor products. This results in high costs, inefficiencies, massive errors, challenges with compliance and risk management, and in many ways, it challenges our ability to better serve customers. Knowledge Graph provides a strategic solution to remediate many of these challenges. First of all, Knowledge Graph relies on a common semantic model, which provides a common language that not only humans could understand, but so can machines. Secondly, we have an opportunity to create standardization in how we validate our data so that we have standard, reusable, smart data quality rules as an opportunity with a Knowledge Graph. Then we create the opportunity to create a layer of knowledge over these many diverse physical data assets across our siloed environments, which I'll talk quite a bit about later. And then we have the opportunity to create holistic data and linkage across many of these disparate data sources. So also with Knowledge Graph, we have the opportunity to finally realign the disparate protocols for data at rest and data in motion. The JSON LD standard is a way of aligning our payloads with our core Knowledge Graph models if they're developed in RDFL. We also have the opportunity for improved search and understanding and governance of our data. This also provides an opportunity to better comply with regulatory management and future-proof our evolving challenges where we can create a better bridge to machine learning. This can better ultimately serve customers, fulfill regulatory compliance and risk management, reducing costs and errors, increasing efficiencies, and improving his insights. So I'm going to talk a bit about the knowledge graph trajectory. So at the bottom, we have things that humans understand, and at the top, things that machines understand. And this parallels basically the expressivity of information models. So we start in 1970 with the relational model. Tables represent entities, and columns represent attributes in these entities. We fast forward all the way into around 2004 with the advent of the semantic web language stack, which provides a standardized language, a semantic language that allows us to represent concepts and the meaning of data, an area called knowledge representation and reasoning and ontology. We call this knowledge graph 1.0, things in Google's term, not strings. We move up a few years later, around 2011-12, into what we might call knowledge graph 2.0, which is now the convergence of machine learning with knowledge representation and reasoning, and it's realized by leveraging the insights from ontology learning algorithms, entity classifications, link predictions, and other probabilistic inferences can then be inserted back into the graph for traversal and query. And now we have at the top level, we move from predicted things to embeddings, which now converges deep learning with knowledge representation and reasoning and machine learning, where we're taking the meaning of the nodes and the edges in the graph, and we're running different encoding algorithms to generate graph embeddings and basically semantic points in a vector space model that we can actually query directly using linear algebra. We'll call this knowledge graph 3.0 for a much heightened level of precision of querying these points in lieu of querying the more classical semantic graph databases. So utilizing the knowledge graph will reduce costs, increase efficiencies, and accelerate time to knowledge. So the x-axis you can look at as an increase of cost and decrease of efficiency, and the bottom axis is the x-axis rather, is as business domains, applications, and databases increase, we're going to see some increases of columns. And then on the other side, we show time to knowledge, which we want to see diminishing in time. So we can see here this linear curve, more likely in reality, it's parabolic, as new physical data elements are introduced as a result of the growth of applications and databases. We see this great rise. However, with the growth of knowledge graph, we see something very different. The introduction of net new concepts are dramatically reduced over time because there are so many new concepts in a knowledge graph. These concepts will map to many, many different bespoke physical labels that mean the same thing. So in the very beginning, we'll have some increased investments in knowledge graph in order to model the knowledge graph to reflect the reality of business in the organization. But as we further develop this initial cost, which also reflects high degrees of reusability, the investment dramatically goes down. However, as we compare it to our legacy world, our costs are actually rising over time. And the only way to really get a hold of these uncontrollable costs for data governance and data management is to move to a knowledge graph where we can use a more finite set of concepts to gain hold on this. Now, where do we get these knowledge graphs? We don't have to build them from scratch. The Enterprise Data Management Council is a nonprofit financial industry trade organization that focuses on data quality, data management, and now on creating open source knowledge graphs that are based on the semantic web language stack, OWL and RDF OWL, that allows certain concepts to be defined as a industry standard, particularly in the capital markets and business entities area, where the information has to be exchangeable with regulatory agencies and other institutions, and it's very highly well positioned for standardization. So FIBO has taken a step forward to create these open, reusable knowledge graphs so that organizations that want to use this do not have to reinvent the wheel and can leverage information that's already been developed. So FIBO can help organizations jumpstart their knowledge graphs. And the way this works is that as an enterprise wishes to develop its own specific areas of competency or domains, all it needs to do is import the interested FIBO ontologies and simply reuse it. And the ontology allows you to extend it with the organization's own specializations, so that the FIBO ontology could be used for direct import, or it could also be used as a reference model. So what is a knowledge graph environment? So the core foundational building block of the knowledge graph is the ontology, and the ability to link and integrate related ontologies and standardize it at an enterprise level is what we would call an enterprise ontology. And these enterprise ontologies should be viewable by users in order to understand the relationships of the nodes and edges, essentially the concepts and their relationships. And the first major opportunity for utilizing this ontology is in the area of creating a layer of knowledge over our physical data assets. So this is what I'm going to talk about further. It's the notion of a semantic data catalog, where we're able to, through various tools, to profile the source data and map it to the equivalent concepts in the ontology that can then be more effectively searched and queried for understanding. This uses human intervention for mapping, but can also leverage machine learning in order to accommodate the mappings to these source data elements. So I'm going to focus mostly on this, but to finish out the architecture, we would include what we would call a semantic curation process, which will leverage the relationships found in the semantic data catalog that identify the varieties of physical data assets that would be ingested and harmonized into the common semantic model. Various processes are executed to curate and validate the data to ensure high data quality, and then other rules are executed to transcend the impedance mismatch between a relational model, for example, or a spreadsheet, and a semantic model. So that is what we call transformation, and then ultimately materialization into an operational knowledge graph, which examples of that were demonstrated a bit ago by Jay, and machine learning also plays a significant role in this area, because machine learning then can iterate through the nodes of the knowledge graph for certain entity node resolution, link prediction, classification of various nodes and relationships, to predict new relationships and infer new relationships from a prior set of empirical information that's ingested, as well as positioning for encodings and embeddings based on what we call the Knowledge Graph 3.0. This would create a consumption layer that positions users, again, data analysts for business intelligence, as well as many data scientists, that can leverage the knowledge graph to basically ask questions and identify a subset of information from within the operational knowledge graph or from the various legacy data sources or enterprise data lake environment to extract into various forms, including other graphs where we may have more homogeneous graphs that might be formed for specific use cases like payments or fraud, as well as a larger embedding space that can be queried and interrogated. And much of this can be done also on demand through messaging services by applications which we would call knowledge as a service, which can leverage the JSON LD protocol or the GraphQL, for example. So we're going to concentrate for the remainder of the presentation on the semantic data catalog and what that is. So this provides a very important and much needed capability for the enterprise. And so we're going to cover what some of these key features are. So first of all, the semantic data catalog utilizes a common standard reusable information model, aka the ontology, that describes the meaning of enterprise concepts and data. It provides a highly expressive metadata capability as well that also includes annotations for data privacy and information security classification. And this is all integrated into the core information model and linked into the data at the same time. It also should provide an inventory of physical data elements that are linked again to this core standard knowledge graph model that positions us for semantic search over that inventory, better understanding, and then later extraction. Including in this as well is the ability to have accurate data provenance and lineage that we can query. Executable data quality rules are a key aspect of a semantic data catalog that allows us to define rules at different levels of abstraction that can be executed against the information that's ingested into the graph in order to ensure high data quality as well as capture various metrics on data quality. And then lastly, the ability to utilize the catalog to ask questions at very high levels of abstraction in order to, again, identify the physical elements in the source systems or the data in the knowledge graph that can be used to extract information. So the first important piece of a semantic catalog is, first, we want to differentiate between conventional glossaries and dictionaries and catalogs, semantic catalogs. So a conventional glossary will have a term or a label and a description. It's very much a singular monolithic statement without much relationship that you'll see the next example for the same piece of information, an account. A knowledge graph model is going to provide much more of a multidimensional view where that account concept will also have the same definition, but in addition, it shows relationships to related concepts that provide this multidimensional view. So to better understand the core concept, it helps to look at all of the related linked concepts to get this more holistic view and to see that concept in context with other concepts. As you could just see, it's intuitively obvious by looking at all these key relationships that make up the account. So this is going to ultimately become a system of record for definitions, and this also can be operationally viewed. So as I just said, a knowledge graph will emerge to become the system of record for business concepts and definitions. It will be fed by the various subject matter experts that work on glossaries, information models, as well as it will be highly influenced and fed by other industry ontologies like 5.0 and others that are emerging, as well as other standards. And the actual glossaries will then simply be an extraction from the core enterprise level ontologies. Knowledge graph is therefore the basic building block for the semantic data catalog that helps us answer questions like, A user might ask, where are credit card account identifiers across different systems? Or what is the information security classification of credit card account identifiers? With legacy technology, we'll have simply many bespoke labels for a particular column, and many of these include more than one columns in tandem, where in this case, we have an account type plus an account number. And quite often, because of the massive size of this, we need these metadata repositories to identify these elements, but the challenge is that they're not always retrievable or identified within the metadata repository. They get out of sync because it's a third-party product that's differentiated from the data itself. And then we may also have to rely on security policies to determine what is confidential, what is restricted, et cetera. The problem in the legacy world is there is no general model over technical metadata. Fast forward to the semantic data catalog is where we can say that this is knowledge graph plus metadata, where we'll have the model define the semantics of an account identifier. And we might see in this model that a card account identifier is a kind of account identifier, and a credit card account identifier is a kind of card account identifier. And the linkage between the concept of a credit card account identifier and the various bespoke data elements basically fulfills this equation where we can query the knowledge graph to locate the physical data assets. In addition, the knowledge graph has additional attributes where at the parent level of an account identifier, we might say it has information security classification confidential, which says that anything that is within the set of account identifiers, such as credit card account identifiers and deposit account identifiers, et cetera, will all inherit the attribute of its parent's parent that each of these identifiers are all confidential. So we can then draw an inference that all of the things that are credit card account identifiers are also confidential, and this can be queried. So with the knowledge graph, concepts describe columns. We could also look and ask other questions. We can look at the layer of knowledge over physical assets. What types of customers are in the customer table? Where can we find organizational names in this database? We may have a table customer with a simple column name called name, the knowledge, and we may not really know what is inside this name column without looking at a metadata catalog or asking a subject matter expert. It's often tribal knowledge. The knowledge graph captures the tribal knowledge and creates institutional knowledge where we can link these semantic chains of meaning that the customer table column name is really a customer whose identity is a person who has a personal name and perhaps a first and last name value. But in many cases, we've found that perhaps it's not only a personal name, it may also be an organizational name, and the knowledge graph can reflect that. Other questions, such as what physical elements are associated with the account in the marketing database. So we see the full semantics of account with all of its relationships, and we can then create these linkages that define all the different columns that align with different concepts that relate to different tables in this marketing database. So we can get the full answer by asking at the top level. We could also do data assets to concepts, where we might ask, what information is contained in the marketing database customer table? So we have the graph that reflects the customer table in the marketing database. We then can see that there's a linkage in the graph to customer, which has links to many of these other relationships. So we could see in this case that for a small set of columns, we can look at the semantics of the graph to again see that a customer has identity of person, where we may have a social security number with the relation has TIN. We may also have a customer whose identity is an organization whose predicate has TIN is tied to an employer identification number. These are very different things, but they may all be stored in the tax ID column in the customer table. So the semantics of the graph are very important to pull the meaning out of what is in these physical data assets that are often hard to crack. We could
David,
also
you have
ask
5 more
some very
minutes.
basic questions. Sure, thank you. Where can personal contact information be found in the marketing database? So again, we could see the various abstractions, and these abstractions do not exist in these bespoke labels. They're very difficult to crack, and therefore it's highly time-consuming for analysts to be able to pull this higher level abstraction together without a knowledge graph. That makes it extremely easy. So a semantic graph will also provide data quality information. So we have an additional standard called Shackle, which defines validation information, which is a knowledge graph itself that's executable, where it's able to interrogate information. In this case, Bob is a type of person whose tax ID number 12345ABC doesn't follow this standard pattern. It generates a validation report into a knowledge graph with an explanation so that we can then do further metrics in the data semantic catalog, where we can look at the data quality metrics for a particular source information to determine what the level of quality of that information is. So we can standardize data quality metrics. We also need semantic search capabilities in the semantic data catalog. So given a string value, predict the concept. So here we may have a misspelling of an interest rate swap, and we want to predict the right concept in a knowledge graph. There are many lexical algorithms we can apply, but there's also equivalents that only demand semantic relationship. So a vanilla interest rate swap is really the semantic equivalent of a fixed float interest rate swap. And we use techniques like concept vectors or embeddings to predict the right relationship or concept that's in a knowledge graph. Also, given a predicate and a concept, predict the concept. So a contract is a type of what? The answer is it's an agreement. This is a technique that can be leveraged by utilizing concept and predicate vectors in the graph. Or a legal entity is organized in a jurisdiction, or what is incorporated in a jurisdiction? It's a corporation. Or what has biographical information? It's a person. These all use concept and predicate vectors, and compare this to more of the conventional full text search methods in many of the legacy metadata tools, where you'll get a bag of words coming back that have string matches, and many of the answers could be just totally way off. So what we need is semantic search and semantic alignments. So the last slide here is how is this done? Knowledge graphs provide a great training set for accurate embeddings, where we can encode the semantic meaning of the concepts and their relationships and create these concept and predicate embeddings, which can then be further utilized using techniques like graph representation learning, which translates the graph and all of its relationships into a knowledge graph embedding space where various search capabilities, semantic search in particular, is queried, and resulting relationships come back really at the speed of linear algebra equations. So all of these capabilities are needed for a true semantic search, a semantic data catalog. And thank you very much for hearing my presentation. That concludes my remarks. And I can be reached at my email or through LinkedIn. Thank you very much.
David, thanks for a very, very informative talk. I'm sure the students will have a lot of ideas, found a lot of ideas buried in there, and can go back to your talk and look for like interesting projects to implement. So with that, we have 20 more minutes. So we can open it up to a broader discussion.
I have a question for all the panelists. We here have an interesting use case among the panelists because their respective companies are exchanging data. And I'm really curious to know is there a best practice? Is there a data exchange format? Is there a shared ontology? How are you exchanging data?
Let me
jump
start
in
first. Sorry, go ahead.
Quick response. So the ability to link disparate information from diverse organizations is really the underlying use case behind a semantic graph capability, where the ontology represents the common concepts that can then be linked to the different disparate elements in the diverse feeds of information coming in from different organizations. This is a prime use case that the EDM Council, for example, is discussing with many of the regulatory authorities, the CFTC and the Federal Reserve Bank, the Bank of England, the European Central Bank, and many other regulatory authorities, because during the financial crisis, the opaqueness of data across different financial institutions created tremendous challenges for supervisory authorities to see the risks of different portfolios across organizations and ultimately the systemic risk across the financial industry. So the goal to create this harmonized common language across finance is the underlying use case for FIBO. And so the more adoption of FIBO, likewise with protocols like JSON-LB, many different disparate information can be pointed to its common semantic root in a payload. So this is one way to do it, but then I'm sure my colleagues on the panel could also talk about machine learning methods through NLP that can also do certain semantic alignments.
So Jay, what's your take on this?
Yeah, Vinay, if I understand your question right, I think we have to integrate a lot of data from 20,000 plus financial institutes. Our approaches was very traditional, which is standardization, open specification. So in this case, there is a protocol, Intuit was one of the leading one developed 20 years ago called OFX. That's a lot of times we use that to exchange banking information. Those are very structured data. Those are does not necessarily need knowledge graph. It's really just exchange data in the standard format that everybody can understand. The other part is imagine we exchange data with governments, right, with RIS, and governments publish those standards. For example, there is an XML-based model called MEF. That's how government accept all the e-file, and that's how they have a very clear, rigorous definition of what is a money, what is type, what is a taxpayer. So in some sense, in our world, at least right now, we rely a lot of those conventional standardization to exchange data. Now, knowledge graph will be the next thing, but right now, again, for me, one of the personal experience, in corporations like Intuit or the other financial institute is really most of the engineer, it's about education. Most of the engineer, the knowledge graph ontology is way over their head. For them, there's a lot of over specification, the complexity, they don't see the benefit of the complexity. So that's why I start with something smaller, so start with something more concrete. It's easier for to adopt. But as I just said, I went to this knowledge graph conference about 2 weeks ago. I think David was there as well. There's good news is the industry, the graph companies start introducing familiar terms. For example, GraphQL is one of the latest development. A lot of engineer already adopted. Using that, try to standardize definition on that is already a great step towards, from crawling to walking before running. I feel like a knowledge graph ontology is ultimately like a FIBO. It's great. It's almost at the run stage. A lot of the companies still at the crawl stage or walking stage. That's how I look at it.
Okay.
All right, I have a question for Jay, actually. So this was on my mind, but I saw somebody in the chat had also asked the same question. We're intrigued by your use of your creation of the computation graph, and as a mechanism for improving the computation, but also doing explanation and so forth. But the question in the chat, which I thought was right on the mark, had to do with the fact that the semantic level of that is still somewhat, it's the same as the computation level. There's a humorous piece about how the IRS forms would look like if they had to compute the solution to a quadratic equation. You take b and you'd multiply it by b to get b squared, and then you take 4ac and subtract it from, and if you try to generate a solution and take the square root of that, if you take the explanation that would come out from that, will be incomprehensible. So the question is, how do you guys, the examples you give are great, but some other examples are not so good if you just follow the computation in the forms. The forms are already a compilation or a programming of higher level tax regulations. Can we just get access to those? Why not the IRS? Why doesn't the IRS publish them at that level? I know there's been some discussion in the IRS of doing that. Anyway, can you comment on that?
Yeah, that's a great question. I think observation is absolutely right. And then to prepare this talk, I have to resort to very simple examples. I cannot give too complicated example. There's a lot of the trade secret behind. But I think overall, you're absolutely right. And the way, I mean, a lot of those, when we actually work on those, we start with the fundamentals. And then majority of the calculation is like that. But you're absolutely right. Some of the thing is semantic level is so low, you explain it, so what? I think we're actually developing real customer-facing product. We got a lot of feedback from customers. So again, we're very customer-driven. So the thing you mentioned about sometimes we do short-circuit those explanations. We don't automatically from the raw level. We actually elevate them to a higher level. So that's where a lot of innovation, a lot of it's in the detail. It's not simply just take whatever is there. It's also give content curator a high level construct. They can group a lot of those things to explain in the group instead of explaining individual statement. That's actually all the things that working together to provide the meaningful explanation to people. Yeah,
that's a great answer, and I'm glad to hear that that's how you're proceeding, because I think that does directly address the problem. However, there's the other half of my question there, which had to do with, well, the IRS publishes other vocabularies and things for these XML formats. Why not? Why doesn't the IRS publish the text code at a formal but higher level than the one that appears in the form? Is there any progress there? Is there any pressure there that can be applied?
Sorry, we're compliance. We're working with IRS. To be honest, I mean, if government does everything right, I think your tax is automatically done, right? So anyhow, that's why again we are helping with government as well, IRS, to simplify for us. Yeah, we want to simplify it. We want to make sure people, basically they can get the thing done, as I said, done right, with confidence, with minimum work. IRS already did a great job trying to map complicated tax code into some easy to follow form instruction, almost like step by step. Manually, somebody can do it. But as you said, it's a tremendous amount of work. I really appreciate all their work. Of course, we're compliance. We have to follow whatever they publish, right? We cannot take our own liberty to interpret those tax codes. But all these technology, if somebody from government is, it can be used, as you said, can we go to a step higher? But I think that the other thing is we do need RIS, because tax code, for whatever the nature of that is messy. Sometimes it may not be logical. So we definitely need ways to figure out what's going on there. What are the different exceptions? What I learned from by working for Intuit for this year is oftentimes the really complicated thing you look at it doesn't make any sense, but it's a result of interest group. It's a result of all the complicated layer of things on top of each other. So having a knowledge-based system, if we can develop that, can actually help understand all these complexities, how they depend on each other, what things make sense, what things does not make sense. But based on where we are, I think it's a long way to go. Again, for Intuit, we're compliant. Our job is to make sure the normal user does not have to really read through the instruction. They can get their taxes done without any work, basically. That's our goal.
Thank you.
Thanks. That was very useful.
I have a question for Apur. I know that JPMorgan has made a huge investment in AI research, and they have a huge lab on the East Coast headed by Manuela. Would you be able to shed some light on how the work in the AI research is intersecting with the work that happens in your team and in San Mateo?
That's a great question. So we are more of an applied AI team. So I think about Manola's team is working on solving or attacking problems that we need to solve as an industry in the next 3 to 5 years. A big parts, for example, especially in the trading, one of the biggest problem hampering the growth of algorithmic trading to the next level and applying AI even more deeply is a lack of good simulations, market simulation. So this is one area that, but creating good market simulator, okay, market simulator is easy, making a good one is extremely tough. So this is an area that she's working on. Where we partner with her is on some of the much more near-term simulators that we can productize for our traders to test some algorithms. This is where our team gets involved. So part of my team is focused on taking some of the simulator that came out of our team and making it useful for some very simple reinforcement learning algorithms that we are trying out. So that's how we work. So and again, her success is solving major problems in the next 3 to 5 years. That's how I sort of differentiate.
So I had a question. So this is financial services is at the heart of all the COVID related sort of problems you're facing. What are your companies doing? Are there any interesting projects that have come out of these hard times?
Yes. Let me start first. I think at Intuit we really care about our customer because, as you know, we cover those 5 million small business. They got hit the biggest by this COVID-19 crisis. So there's a couple of things we're doing. Number one, we actually using the same technology, we actually quickly create those what if scenario analysis to help you quickly identify whether you're eligible for aid. I mean, that's one thing. You think about those are a bunch of rules, but we are able to code it really quickly using this, and they have a very dynamic, personalized experience to walk you through what's needed, what does that mean to you. So there's a product called Aid Assist that's actually freely available. It's a free tool everybody can use. Second part is we are one of the few companies, finally, we were never in the official loan business. Our company made a decision to enter the loan business just to lend the help to our small business customer. So we have one of our product from small business group actually is providing loans to the small business because we know their accounting, we know their nature of business, we have a better way to assess what they need and how we can help them. So that's really the second part. The third part is, again, also a lot of those loan programs also integrated with government's PPP and so on and so forth. So again, we've done a bunch of things very quickly because, again, if all customers are not doing well, they are not going to use our product. So we really care about their existence, or we want to help them to survive or thrive after this crisis.
And let me just add, from a Wells Fargo point of view, that Wells Fargo is perhaps the largest lender to small businesses in the country, I believe. And the company is entirely focused on helping small businesses survive the pandemic. And Wells Fargo has been front and center of supporting applications for PPP loans to small businesses. It's absolutely essential that these businesses survive through this pandemic. It's really the lifeblood of the American economy. And so we're very focused on that.
And I think on JPMorgan side, again, the saying internal is don't let a crisis go waste. So a lot of application of AI that we have been thinking about or mulling over, we are increasingly using this as a way to sort of accelerate that development. To give you a few examples where we applied. Are you guys able to hear me? Is there a lag?
No, we're able to hear you.
So one example I'll give you where this is not as much on knowledge graph, but AI was applied was, if you notice, almost every small and medium business submitted a documentation to apply for a loan. And the funny thing is, or interesting thing I would say is, a lot of these documentation was essentially in a lot of cases a spreadsheet with their payroll. And and from all the way there, so highly less sophisticated, all the way to documentation to with W-2s and tax form. So when you're looking at this kind of data and you have to approve all these loans and very quick cycle, you are essentially using our AI to understand past this information and then utilize and make the decision. So that's where we utilize a lot. The second area where you probably noticed this, we did not do this, we could not implement in time, but area where you probably heard about a company and it's franchisee applying for the same loan and getting approved multiple times. And if you have information about a knowledge graph which has controlling information about who the company is and the parent, this is very easily able to detect. And this is one area where we have the information, but we haven't fed it into a knowledge graph to quickly classify that, hey, these two companies are essentially controlled by the same entity and should not be given two separate loans, but should be given one. So those are some of the, and so again, as part of this crisis, we use that as an opportunity to accelerate application and development of that knowledge graph in that division. So those are some of the ways we are utilizing.
Thank you.
So David, I know that the FIBO is one of the flagship ontology projects in the financial domain. And I'm curious to know where you see the biggest adoption challenges. So like if I were to say, go to Intuit or JPMorgan and tell them that, hey guys, you should be using FIBO. And they would say, well, we don't need it, right? So I mean, what story do we tell? Or another way to think about this is that whatever is the current state of semantic modeling in fintech, what's the next step that we should be thinking of?
So when we started developing FIBO, there really was very little precedent or exemplars of large knowledge graphs, certainly in finance, but also across many other industries. FIBO was started around 2011, 2012 timeframe. So initially we focused on FIBO as a conceptual ontology that describes the meaning of many different artifacts of finance. As we saw more focus on FIBO adoption, we came to realize that more and more of FIBO would be used operationally. And so in retrospect and looking back, we could see that these ontologies could be better layered for the future, where we have more of the skeletal structure that can be used to identify operational linkages of critical elements that could be separated from more of the very abstract conceptual representations that are in FIBO. So perhaps that might be a future FIBO that would be much more layered and leaner and meaner in that sense. And also there were some of these other abstractions that could have been simplified. So I think that the initial sticker shock from people starting to get their arms around FIBO is its complexity. But FIBO is also quite an asset, particularly in the area of capital markets, where financial instruments are very well articulated and laid out. In other areas, I think there could be a lot more simplification. But in general, I think it's getting over that massive impact of understanding it. So there are lots of tools that are emerging that make ontology viewing a lot easier and more digestible. And so I think we'll probably see FIBO evolve in the future, as it also will transition to being crowdsourced from when it was initially built from a small set of very highly skilled ontologists to something that's going to be more reflective of many larger dispersed groups of practitioners that want to contribute to 5.0, and we're developing a community process to support that.
Well, thank you. We're actually almost out of time. Maybe we can take 30 seconds for each of the other two panelists to make a quick closing remark about where do you see the future? What's next for you? Jay?
Let me start first. I think the future is definitely, as I said, I'm really passionate about knowledge graph. I think a knowledge graph reached to a stage is very practical. I still remember the provocation I shared. That's my belief, and that's what we try to prove out. I think knowledge graph will be the foundation to link both symbolic AI and also machine learning together. I hope we all can, whatever the insight we generate, all feed back into a knowledge graph instead of just one-off use case for that and that. So for me, the power is glue them together, but at the same time require people like David, 5.0 to make it open, make it, cross-sourcing, make it easily approachable, breaks down the complexity for adoption, map to familiar things the most engineer can understand, and that's where we see the future, the future of knowledge graph will advance greatly.
Okay, Apoorv?
Tim, I think I'll second a lot of the things Jay said, but I probably don't not there yet in terms of the third wave of AI is based on knowledge graph. But I think I would say knowledge graphs and we'll see a second resurgence as I think the future of AI is essentially combining symbolic systems with AI, machine learning. And I think that's where I am very bullish on increasingly. I see that in real life and in the interest in knowledge graphs within the firm. There was a lot, as I said in the beginning, 4 or 5 years back, this was a big knowledge graph effort that got killed. I don't think that will happen again at the firm. And so I think I'm very bullish, and I think this is and again, whether we will go to an industry knowledge graph with this huge need, I think between firms that exchange data, I think a lot remains to be seen. This industry is not very good at collaborating across, but I think there's a huge need. I do agree what David is trying to do. I think there's a huge demand and interest, and pain point is real, but it remains to be seen in terms of how far we go as an industry in sort of creating a much more easy way to collaborate on data sharing.
Okay, I think with that, we should close for today. Thank you all very much for your valuable insight. And we will adjourn for now, and we will convene again next week, same time. Thank you all very much.